C'est bon, je peux commencer? Ok, super. Bon, ben, bonjour à tous. Il faut que je parle en anglais, c'est ça? Bon. Okay, so today we have the pleasure to welcome Giulia Cusin, our new colleague. As you may know, Giulia was hired by CNRS in 2021 in the astrophysics section, but she just arrived physically at IAP about less than a month ago. So it's really your introductory lecture to our institute. And she actually started to come to the Institute in 2015. At the time, you were a PhD student in Geneva University, working with Michele Maggiore and Ruth Durer on modified theory of gravity, non-local theories. And Giulia was a little bit fed up by all this theory with no clear connection to the observed world. So she came to the Institute for a month, something like that, to work with Cyril Pitrou and I on CMB, anisotropies, and trying to understand the difference, the difference of signature between kinematical and geometrical dipole. And I think you loved your life in Paris. You loved it so much that you wanted to come back, and we had more and more projects, and we had an easy way to communicate, the three of us. And then you came back, I think 2017, then you came back for a 7 month period, and we started to work on the astrophysical background of astrophysical gravitational waves. Trying to define it, to compute it, to predict the signature. So the three of us, and then it extended because we need some astrophysical input. And this is when you started to meet with Irina and work with Irina. And this is a topic that you push for the past years. Then Giulia went to after her PhD, you went to Oxford for a postdoc. You worked with Pedro Ferreira, and you started to collaborate with people from the LIGO collaboration in order to have an idea of the noise and the kind of detections that would be able to be done with LIGO and then LISA. And then today you are part of the Einstein Telescope collaboration, and you are the head of the, what is it called? The astrophysical background, blah, blah, blah. You told me the division. It's a division. It's not a working group. It's a division. So this is basically, after this postdoc in Oxford, you went back to Geneva. You got this Ambizione scholarship, which is a very famous scholarship in Geneva, a 5-year scholarship to actually have your own small team, because you hired a PhD student on this scholarship. And this is why she stayed for 1 more year in Geneva after she was hired by CNRS. So the main topic of Giulia is astrophysical gravitational wave background. You're also very interested in lensing of gravitational waves in different situations. And for those who don't know Giulia, she didn't start as a physics student. After you graduate, you went to philosophy, and it was a good way to do, because both her parents are physics teachers, and she wanted to do something different, so not physics. She went to philosophy in Padova University, and after a year or so, you were not satisfied by philosophy, and she came back to physics. So you can also discuss with philosophy with Giulia, but I think that now I'll let you talk about your research topic and what you are going to continue at IAP in the coming years. The stage is yours, Giulia.
Can you hear me on Zoom? No? Fine. Do I need to use the mic there? Can you hear me now? Here, yes. On Zoom? Yes. Okay, good.
It's good on Zoom.
Great. Okay, so, well, thanks a lot, Giulia, for this introduction. So I wanted to say that, okay, I'm quite new here, and I'm very happy to be here in IAP. IAP is a place where I spent a wonderful time during my PhD and after, and I've always enjoyed, appreciated the scientific environment in the Institute. So now I feel honored to have become part of it. So today I will present the main results of a research line that I started a few years ago when I was here in Paris. It started with Jean-Philippe and Cyril Picot. And then I continued during my postdoc. And our goal was to provide a framework to fully characterize the properties of a stochastic background of gravitational waves of astrophysical origin. Okay, so if you have questions during the talk, don't hesitate to raise your hand and to ask, don't wait to the end. So we'll keep it a bit more interactive. So the, oh la la. A technical problem. Okay. So this is a kind of a standard slide with which every gravitational wave talk starts since a few years. So we know that we are in a new era of gravitational wave astronomy. We had a few years ago the first detection of a gravitational wave event from a merger of two compact objects. This detection by the LIGO-Virgo collaboration was then followed by many other detections of similar events. But in the next few years, we will have a new generation of gravitational wave detectors. And in total, we will cover a very broad frequency band. We cover almost 10 orders of magnitude in frequency. And we are looking at a totally different frequency window with respect to the one we have access to with electromagnetic radiation. Because if I had to plot the electromagnetic spectrum here, I had to add, to go outside this slide here on the right at much, much higher frequencies. So in what we will have in the next few years, so now we are working in the Hertz band with the LIGO-Virgo collaboration, and we are using Earth-based detectors. In the next few years, we will have a third generation of detectors, Einstein telescope and Cosmic Explorer. Then if we want to detect waves with a longer wavelength, then we need to go to space. And this is the idea of LISA. LISA is a mission funded by ESA that will fly in a few years. Then if we want to go to astronomical wavelength, then we use pulsar timing arrays. And when we look at very, very low frequencies, then the idea is to measure and set constraints on tensor modes from the primordial universe, looking at CMB polarization. So now I will illustrate one after one, quite briefly, each one of these experiments and explain which type of astrophysical sources we expect to detect in each frequency band. So let's start from the Hertz band. So as I said, in the Hertz band, we use ground-based interferometers. LIGO-Virgo, for the moment, we have a network composed by two detectors, two LIGO detectors in the US, Virgo in Italy, Kagra in Japan, and we will have LIGO India joining soon. In the next few years, Einstein telescope will be built. This is a European collaboration, and it is an underground detector with a triangular shape. So it's composed by 3 nested interferometers. We go underground, so we improve a lot the sensitivity to low frequencies because we reduce the seismic noise. And so we expect to detect many more sources and with a very high signal to noise. Cosmic Explorer is its American counterpart and is the next generation after LIGO. So there are 2 L-shaped detectors, but with longer arms and with a much better sensitivity with respect to LIGO. So for the moment, the LIGO-Virgo collaboration detected more than 90 binary systems of compact objects, so 90 binary black holes, 2 binary neutron stars, and 1 system composed by 1 neutron star and 1 black hole. And we expect this catalog to become more and more rich as we will improve the sensitivity of the instrument in the next few years. And LISA is a space-based interferometer. So we have 3 satellites in a triangular configuration. The distance between the satellites is 2.5 gigameters. And they follow the Earth. So they follow the same orbit of the Earth around the sun. And they form, so the 3 detectors, the plane of the 3 detectors forms an angle of 60 degrees with respect to the plane of the ecliptic. And with LISA, we are sensitive to frequencies in the millihertz band. And this is an incredible instrument with which we expect to see a bunch of different astrophysical sources. So the brightest sources that LISA will see, here in this slide, you see the sensitivity curve of LISA as a function of frequency, and different sources that we expect, the strain of different sources that we expect to see. The brightest ones are massive black hole binaries. So black holes in the center of galaxies that are in a binary system, they orbit around each other and eventually they merge. But with LISA, we will see the final phase of the spiraling, so the final spiraling phase, and then the merger. Then we'll see thousands of galactic white dwarf binaries. These are almost monochromatic sources. Some of them will come with an electromagnetic counterpart. And then millions of binary white dwarfs that are not resolvable, and they form a background, irreducible, called galactic background. And what we do usually is to deform. So this is the background from galactic systems. We deform the sensitivity curve of LISA to take into account that we can't get rid of this astrophysical contribution. Then, if you are lucky, LISA will also see extreme mass ratiation spires. So these are binary objects where we have a massive object and a stellar mass 1 orbiting around it and eventually falling into the massive object. And the spiraling phase of the evolution of stellar mass binaries, these are the systems that then go into the Hertz band, and LIGO Virgo will be seen by LIGO Virgo in the merger phase. Then in the nanohertz band, so a longer wavelength, the technique that is used to get a detection is using pulsar timing arrays. So we monitor the period of an array of pulsars, and the perturbations in the period is an indication that space-time between the Earth and the pulsar has been deformed. To claim that this deformation is due to a gravitational wave, we need to have some form of time correlation and space correlation between different pulsars. And in particular, we need a space correlation that is very particular, that is almost quadrupolar, and is described by an analytic curve called the Ellingstow's curve. With pulsar timing array, we expect to see a stochastic background from the merger phase of the evolution, sorry, the spiraling phase of the evolution of massive compact objects, and possibly other types of primordial backgrounds. Okay, so here I finished my overview of the different experiments that will be active in the next few years and are active now. And I've used multiple times this word stochastic background. So everybody probably here has an intuition of what a stochastic background is in the context of electromagnetic radiation. For gravitational waves, is more or less the same thing. So it's the incoherent superposition of signals from different sources around us in the universe. And the word incoherent means that we don't have any phase information when we look at the background. For both electromagnetic radiation and gravitational waves, we can distinguish a background of cosmological origin and a background of astrophysical origin. The background of cosmological origin for electromagnetic waves is the CMB, the cosmic microwave background, while the astrophysical counterpart is the cosmic infrared background, so the electromagnetic radiation from all galaxies around us in the universe. For gravitational waves, we have cosmological backgrounds that these are tensor modes produced by different processes in the early universe, while the counterpart of the CIB is an astrophysical background of gravitational waves. So inside each galaxies, there are gravitational wave sources, and then here on Earth, we collect all the signals from all these sources. So in the same way as the CIB is a foreground for the CMB, so we need to properly study and characterize it if we want to subtract it and look at what is left. Then an astrophysical background is a foreground for cosmological backgrounds. So it is an observable by itself, rich of astrophysical information, but we also need to properly study it if we want to hope to see primordial contributions. So this is a snapshot of the evolution of our universe. Time flows in this direction here. So the beginning of our universe was very hot and dense, and then it expands, it cools down, 4 structures are formed. And using gravitational waves, we can get a direct information going back in the past, at most up to the last scattering source. Because before this instant of time, photons were belonging to a hot and dense plasma. They were scattered all times, so they can't travel freely and reach us today here. On the other hand, if we are able to detect primordial tensor modes, then we will get a direct information about the very first instance of time of the evolution of our universe. Okay, our universe expanded, and now it's cold, and we have structures here. And when we have a population of astrophysical sources, we can decide whether we want to focus on those sources that are particularly bright and can be detected individually, or we can just listen to the choir of all the signals of these sources together. And this second approach is what we call a background description. So when we look at bright sources, then the quantity that we measure is a waveform as a function of time and frequency. And by comparing our template for the waveform to what is observed, we can extract the intrinsic astrophysical properties of my source. For a stochastic background, what is measured is not a strain, it's not a waveform, but is an intensity and polarization map at different frequencies. And the astrophysical information encoded are the collective astrophysical properties of a given population. Of course, these two approaches are different, but they are complementary. And it's very interesting to use them together. And I will get back to this because combining these two approaches, we can extract astrophysical information about a very faint subpopulation that can't be seen in any other way. Okay, so there is a technical difference in the way we detect resolvable events and a background. As I said, for resolvable events, we measure a strain, and then we compare the output of the detector to our template. We compute the likelihood that the template matches the signal, and then we change the template until when we maximize the likelihood. For a background, we can't do this because the strain in the time domain looks like this. So it's a very hairy plot. It's very similar to white noise. And it is typically within the instrumental noise threshold. So we can't apply match filtering techniques to extract this. And what we do is to match the output of a network of detectors. So we need at least 2 detectors to extract a stochastic background. This means that from a theoretical point of view, we don't have to focus on a strain description when we describe a background, but we need to build and to model quantities that are quadratic in the strain. Now, I want to enter into this in more details, but before this, I want to show you these pictures that is produced by Tanya Regimbourg in Annecy. And she simulates a population of binary neutron stars and binary black holes in the Hertz band. So in the spikes here, green are binary black hole mergers. So the duration of the merger phase is very short. So we see a signal that is called popcorn. So you see spikes, and then the merger is off, and you have to wait for another merger to arrive. So events have no time overlap almost. For binary neutron stars, on the other end, there is this is the red curve. There is some type of overlap, and all this is mostly within the noise threshold. So to extract this out of the noise, we have 2 detectors, A and B. Each one sees a signal part and the noise part. And then we assume that if my 2 detectors are on 2 different points on Earth, for example, noise, there is no reason to think that noise is correlated. And we assume that signal and noise is also not correlated. Then we build a quantity that is quadratic in these outputs, whose expectation value is what we call signal, and the noise is the fluctuation of this. So the variance of this in the absence of signal. Then if you compute these integrals using the ergodic assumption, it turns out that the signal to noise grows like the square root of the observation time. This means that if you wait long enough, you can extract the signal out of the instrumental noise threshold. And this signal here is something quadratic in age, so quadratic in the strain. Good. So from a theory point of view, we need to build a quantity quadratic in the strain and compute their endpoint functions. The starting point is the strain. Actually, it's the superposition of signals in different, from one that we receive from one direction at a given frequency. This can be decomposed in a polarization basis. And out of these two amplitudes, I can build a tensor that is a complex 2 times 2 tensor called polarization tensor. This is in full analogy with what we do for the CMB. Then this is a complex 2 times 2 tensor. So the most general thing I can do is to decompose it in a basis of the identity matrix and the spin, the Fierz-Pauli matrices. This coefficient here is called intensity. And these other 3 coefficients are Stokes parameters describing the degree of polarization. So if I want to fully describe my background component, I need to study intensity, the spectral shape, the spectrum of anisotropies, polarization, close correlations between all these Stokes parameters and other stochastic observables. And finally, I also want to understand what happens if I use this background description and a catalog description together. So now I start from the description of intensity and anisotropies in the intensity. In the literature, instead of intensity, we usually use the quantity that is strictly related to intensity, that is this omega gravitational waves. This is a dimensionless quantity, and physically it corresponds to the background energy density per units of log frequency normalized over the critical density of the universe. If you want to have a first taste of the astrophysical information inside this observable, you can use this simplistic parameterization. So we integrate over redshift. At a given redshift, I count how many sources of a given type I have. I multiply this by the rate of events of that type and by the spectrum emitted every time I have an event. See that this is a quantity integrated over redshift. So we don't have a redshift information. In this plot here, what is shown is a prediction for a background from mergers of compact objects that is expected to be the dominant astrophysical component in the Hertz band, and the sensitivity curve to omega of different observatories. So for the moment, we don't have a detection. The only thing that we have are upper bounds set by the LIGO-Virgo collaborations. These are the latest bounds from last year. However, now, if I zoom here around in the Hertz band, you see that there is a superposition between the final sensitivity curve of LIGO-Virgo and these predictions. This means that if you trust these predictions, and this is, I mean, predictions are a bit all over the place for the moment, so this is a kind of optimistic scenario, then it means that LIGO-Virgo could get a detection of this background before reaching the final sensitivity. So these are optimistic predictions. However, with the Einstein telescope, we will improve sensitivity in strain of a factor 10. This means a factor 100 in omega. So in this region here, we will go down and we will detect a broader region of this curve. So for sure, with Einstein telescope, we will see something. In the millihertz band, we have LISA. So the background that LISA will see is the inspirling phase of the evolution of binary systems. So if we look at the background in the time domain, we don't have spikes like in the pictures we had before, but we really have an irreducible background. So continuous, stationary, and the standard background we are used to. This is a quite important difference when we characterize it. LISA will see very probably a background from the inspirling phase of the evolution of compact objects. And then finally, if we go to the nanohertz band, then the background is from the evolution of massive black hole binaries. And pulsar timing arrays, different pulsar timing arrays collaborations recently have seen something. So what they have seen is a common process that can be modeled as an additional time correlated term, but they don't see any evidence for a spatial correlation. So if you look at their residuals as a function of the separation angle between pulsars, it doesn't, we can't say that it follows the Hellingsdown curve. The only thing that we can say is that they have seen something, but the origin of this something is still unclear. Okay. In my picture, up to now, I didn't have any direction information. I was using a quantity that was only a function of frequency. Implicitly, I was assuming that if I am the red point here, I am the observer, and I look around me, I receive the same flux of gravitational waves in any direction. Of course, this is an approximation because we know that the situation is like this. So sources are into galaxies and galaxies are embedded in the cosmic web. So there will be a first source of anisotropy due to clustering. And the secondary one, due to the fact that once a signal is emitted, it will feel the gravitational potential of structures. There will be a lensing effect, an effect integrated along the line of sight, a kinematic effect, and so on. So my simplistic situation here at the map level corresponds to a monopole description, while if I allow for a dependence on directions, then I allow for the presence of structures in my map. So now I introduce a quantity that is also a function of the direction in the sky I'm looking at, such that when I integrate it over the solid angle, I go back to my original omega. This quantity is stochastic, so I can compute, as we do in cosmology, its correlation function that under the assumption of statistical isotropy can be decomposed in a basis of Legendre polynomials. And these coefficients here are an angular power spectrum function of frequency that characterize statistically my background. So if I want to predict this observable, I need a model for the anisotropic component of the energy density. So simplifying the situation, I have to think of something like that. So I look at a given direction in the sky with a solid angle. I see galaxies. And then I have to sum, to consider the flux that I receive from a galaxy direction Z, multiply this by the number of galaxies in a comoving volume around this redshift, and then integrate over redshift. Then this, we can write it in terms of a gravitational wave luminosity of the galaxy. This can be decomposed as a product of comoving volume, comoving density. I put all together, I assume an isotropic universe with the cosmological perturbations, and I get something like this. So the only important point of this formula is the fact that there is an integral over redshift, and then there are two building blocks. There is here a cosmological part that depends on galaxy over density, peculiar velocities, and gravitational potentials. And then there is an astrophysical kernel here that is a kind of black box where it is hidden all the galactic astrophysical information. In particular, it depends on the stellar evolution model we assume, the fraction of compact objects in binaries, the mass distribution of binaries, distribution of orbital parameters, and so on. And all these functions are not constrained up to now. The sensible approach to follow is to say, okay, I assume my cosmology to be fixed because we are in the era of precision cosmology. We have a bunch of cosmological surveys that are setting very strict constraints on cosmological parameters. And I fix a reference choice for all these astrophysical ingredients. I derive a prediction for the angular power spectrum. And then in a second step, I go back and modify my choice here, and I check of how much my prediction changes. So this is what we did with Irina a few years ago. And for our reference astrophysical model, this is the angular power spectrum we get. Here I have multiplied it by L and normalized it over the monopole. You see that there is a plateau here, which means that this is going down like 1 over L on large angular scales. This is not surprising because this is the typical behavior of the galaxy correlation function. And we know that the dominant component of anisotropy comes from clustering. And then I have a typical suppression of the anisotropy with respect to the monopole of a factor of 10 to the minus 2. Then we go back here and we change, we explore a bit the parameter space of the model. And we can compute how much the angular power spectrum changes. This is a first exploration that we tried. And we see that if I change the upper cutoff in mass of 10%, I get a fractional difference in the angular power spectrum of 50%. Similar thing if I change the stellar evolution model and so on. Of course, we had fun exploring this parameter space. This is not a complete exploration, but the only thing that we can say out of this plot is that there is some astrophysical information in this observable. So if one day we will have a good sensitivity good enough, and such that we will be able to constrain the CLs, then using this constraint, we can hope to extract some galactic physics information. Now the question is, do we have a good enough sensitivity, which is the typical sensitivity of a network? Before answering this question, I want just to stress one aspect. So for the moment, I was showing prediction for a guy here, theoretical prediction, obtained under the assumption that sources are in galaxies and galaxies are distributed like a continuous field. This is not true because galaxies have a Poissonian distribution in space. So in the same way as we do for galaxy survey, I need to improve my prediction, accounting for the fact that galaxies have a Poissonian distribution. And I do this by adding what we call a partial shock noise contribution to my theoretical prediction. But I need to do something more when we are in the Hertz band, because there we have these popcorn signals, we have spikes. And so we need to account for the discreteness of emission in time. And the way we do this is by adding a time-like shock noise to the theoretical prediction. This component is not there in LISA, because in LISA everything is simple, stationary, continuous, but we need to add this component for LIGO Virgo. And it turns out that this component is quite important in the Hertz band. And the way to extract this out of this noise threshold is using cross correlations, as I will show. But let's go back to the question, which is the angular resolution of a detector network? In Oxford, a few years ago, we tried to answer this question, working out a simplistic and easy to use parameterization to describe the angular resolution of a network, so the noise per multiple. So what we did is to assume a network of detectors, a scan strategy, and then we go on and we translate the noise of a map into a noise on an angular power spectrum. We build a quadratic estimator for intensity and we compute the correlation matrix. And eventually, we have an effective formula for the noise per multiple. That is, so it's a bit the same of what we did for Planck to describe the noise per multiple. So we have a parametric expression that people working on predictions can use to do for forecasts. I want to show you some results. So this is the noise per multiple as a function of multiples. This is for LIGO, Virgo, and Cagra. This is what happens if I add the Einstein telescope to the network, and here what happens if I add also Cosmic Explorer. And what I overplot here is an astrophysical background in the most optimistic case. So this is a background on the edge of being detected by LIGO, Virgo. So with the next generation of detectors, we will probably be able to detect the first multiples of this background. For LISA, the situation is different. The problem with LISA is that LISA is a triangular detector, so it's made by 3 nested interferometers. And the baseline is equal to the arm length. And it is quite small with respect to the wavelength we are sensitive to. So it turns out that the antenna pattern function of LISA, so this is a function that describes the geometrical properties of the instrument, is almost totally even under parity. LISA has a very different sensitivity to even and odd multiples. This is the sensitivity to even multiples, much better to the one of odd multiples. And this is a signal from an astrophysical background. This is unfortunately below the sensitivity curve. So with the one single LISA, we won't be good enough to detect the anisotropy. And I had a very good master student last year, Alexandre Prior, with whom we tried a mental experiment. We assumed to have an infinite budget. And we checked what happens if I start adding LISA detectors to LISA orbit. In this plot from his master thesis, what he shows is, so let's focus on the blue points. This is the sensitivity to the dipole of 1 LISA here, 2 LISA, 3 LISA, 4 LISA, 5 LISA. You see that already going from 1 to 2 Lisa, we improve the sensitivity to the dipole of a factor 10 to the 4. So this was, of course, just a kind of a game, but that's not too far from reality, because there is an experiment that is proposed as a successor to LISA by ESA. This is called the Big Bang Observer, and is composed by 2 LISA-like detectors with slightly smaller arm length, and one configuration, star-like configuration. And with this instrument, we have a much improved sensitivity to the dipole and a much improved sensitivity to the anisotropy. For the monopole, so forget about these curves, but I just want to show you. So this is LISA, the sensitivity to the monopole, and this is the sensitivity of BBO. So we are shifted to higher frequencies, but we have an improvement of a factor 2. So with this instrument, probably we will be able to constrain the anisotropies of an extragalactic background. Okay, so what about cross correlations? People working on large-scale surveys know that a way to get the first detection, a way to extract, to deal with a very noisy map is to cross-correlate with another map that is less noisy with a high level of correlation. And so this is also a good technique to get the first detection of the anisotropy for a stochastic background. And a good observable to consider for this cross-correlation is the distribution of galaxies, because sources are in galaxies. So for an astrophysical background, we expect to have a high level of correlation. On the other hand, this is an interesting observable because it allows one to distinguish the cosmological versus astrophysical origin of the background, because there is no reason why a primordial background is highly correlated with the distribution of galaxies, but this is the case for an astrophysical background. Moreover, it allows to have, so cross-correlating with galaxies at different redshifts, we can pick up contributions from sources at different redshifts. So we can have a redshift reconstruction. And then this is an observable with a much higher signal to noise with respect to the autocorrelation. So with Cyril, we tried, so this is just a toy model. We assumed to have a background from mergers of compact of black holes. And the perfect instrument, so the only source of noise is what I was calling before time-like shot noise in the Hertz band. And this is the signal to noise. It's a function of the angular sensitivity for the autocorrelation. And this is the signal to noise for the cross-correlation. So cross-correlating, we improve signal to noise of a factor 10. Okay, so if we follow the analogy with the CMB study, we know that after the monopole, the first thing that was measured is a kinematic dipole. We expect the same thing to happen also for this observable for a background of gravitational waves. Indeed, up to now, I was assuming that the frame where the rest frame of sources that usually we identify with the CMB rest frame is the same frame where we perform our measurement. This is not true because we move with respect to the CMB rest frame. And so we will have a violation of statistical isotropy. So there are different effects due to our peculiar motion. The most important one is the creation of kinematic anisotropy. So if we have an emission that is isotropic, so we just have a monopole emitted, because of our peculiar motion, we generate a kinematic dipole and then a quadruple and higher multiples that are more and more suppressed by higher powers of our peculiar velocity over the speed of light. Then there is another effect. If we have an anisotropic emission, then we have a map like this that gets aberrated and modulated by our peculiar motion. Statistically, what happens is that in the presence of statistical isotropy, if there is no peculiar motion, everything can be described in terms of a diagonal correlation matrix. When I violate statistical isotropy, I start exciting off-diagonal terms in my correlation matrix. However, this effect is a modulation and aberration of this map by a factor of beta over c. Beta is our peculiar velocity, c is the speed of light. This is something on the order of 10 to the minus 3. So we are considering a very small effect that is modulated by 10 to the minus 3. So this is a tiny effect that we never be able to measure with this generation and with next generation of detectors. So I will focus on this. So if I have an isotropic emission, what I observe, I am the observer, I see this. So I get a creation of a dipole, a kinematic dipole at leading order. And this dipole depends on, so this n is the line of sight and v is the direction of the velocity. This dipole depends on this beta and on alpha, where alpha is the spectral index of my background. A second order in beta, I also modify my monopole and I create a quadrupole. And then I could go on and compute third order, fourth order terms in beta that are more and more suppressed. Let's focus on the dipole. So this dipole depends on beta and on the spectral index alpha. So now if we measure this dipole and we have a way to reconstruct alpha via a frequency binning, for example, then we can extract beta. And this year with Giamassimo Tasinato, we checked that if with Einstein telescope plus Cosmic Explorer, we could get a constraint on beta with a precision of 30%. This is, I find interesting because, as you know, we have two different ways of estimating our peculiar motion from CMB and from quasars, from the distribution of quasars. And the two estimates are out of a factor of 5 sigma. And this is an independent way of extracting the same quantity that could help solving this controversy. Okay, so this is my slide. I've been talking about intensity, cross correlations, and isotropies. Let's talk about polarization. So again, I use an analogy with a CMB. For CMB, we know that there is a key process responsible for the generation of polarization out of an unpolarized flux. This is a process of Thomson scattering of photons of free electrons. And in particular, I need two ingredients to generate a net polarization out of an unpolarized flux. I need a differential cross-section that depends on the polarization of incoming and outcoming wave. And then I need a quadrupolar modulation in the incoming flux. For gravitational waves, we can look at a process of classical diffusion, classical scattering of gravitational waves of massive objects. And these two ingredients are in place for this process because we have a cross-section that does depend on the polarization of incoming and outcoming wave. Now, these are tensors and not vectors because we have a spin 2 and not a spin 1. And then I have a scaling here that is typical of the Raster for the cross-section that is absent for Thomson. This is not surprising because gravitational waves are gravitationally charged while photons are not electromagnetically charged. So this process is more similar to the scattering of two charged objects than to a Thomson scattering. Then we know that we do have anisotropies in the incoming flux. So in principle, I can just close my eyes and push the analogy with the CMB further and consider what happens if I have a distribution of massive objects and I have my flux of gravitational waves that undergoes a process of multi-scattering. This can be described introducing an optical depth that depends on the number density of scattering centers and on the integrated cross-section. Then I can estimate which is the amount of polarization generated in different frequency bands. The answer is that the amount of polarization is very small because the number density of scattering centers is very small. And this means that I can't effectively generate polarization via diffusion. So if one day we measure a highly polarized background component, this is a smoking gun for the cosmological origin of the background. In particular, this means that we have some parity violating generation process in the early universe that generates polarization from the very beginning. So I go towards the end of this list, and I want to briefly explain what we can learn by using together a catalog and the background description. This is a plot produced by Francesca Calore, and what we see here, for Einstein telescope, the distribution of, as a function of signal to noise, of binary black holes. This is the red curve. And here of binary neutron stars. And this is the minimum threshold needed to claim a detection of a resolvable event. You see that the peak of the distribution of binary black holes is above threshold, while the peak of the distribution is below threshold. So most of the population of binary neutron stars won't be detected with a catalog approach by Einstein telescope. This means that if I compute the background budget associated to this catalog and I subtract it from my total background, I am left with what is called a residual background that only captures the contribution from a subthreshold population. And the idea is that by studying this residual background, I can have access to the information about a subthreshold population of very faint and distant objects. I find that this is a nice proof of concept. What is studied in a paper by Martinovich and Perigua is a background in the Hertz band from mergers of compact objects coming from population 1, population 2, and population 3 stars. The population 3 stars are an hypothetical population of very low metallicity and high redshift stars. And if we look at the total background for Einstein telescope, this is the black line. And this is dominated by the orange line. That is the contribution from population 1 and 2 stars, while the contribution from population 3 is totally subdominant. On the other hand, if we compute the residual background, this is the dotted line here, this is dominated by the contribution of population 3. So this means that if we compute this, then we get some information about this population 3. In particular, from the position of the peak here, you can show that you can extract an average redshifted total mass. Okay, so this is a summary. We have seen that if I have a background component, I want to fully describe it, then I need to describe the monopole, the spectral shape of the monopole. And with LIGO and Virgo at design sensitivity, and then for sure with ET, we can detect the monopole in the Hertz band, and Lisa will detect a monopole in the millihertz band. For what concerns anisotropies, if we are lucky and we have a signal to noise detect, so a monopole detected with a signal to noise ratio high enough, then we could have a first map of the anisotropy with ET and Cosmic Explorer together. For sure, these two can say something about a kinematic dipole. Polarization is small, so if we detect a highly polarized background, this can't be astrophysical. And cross-correlating a map of stochastic background with a map of galaxies is an extremely promising way to get the first detection. And it allows one to distinguish cosmological versus astrophysical background to understand which is the origin of the background we are seeing. If we work together with a catalog with a background, we can study a residual background that contains information on a very faint and distant population of sources that can't be seen in any other way. So I like to conclude with this slide. Here there is an analogy between the main steps of the CMB study and discovery here on the left, and what is going on and what we expect to happen for the study of a stochastic background of gravitational waves. The CMB, the monopole of the CMB was measured totally by chance by Pensers and Wilson in '65. And 2 years later, we had the first studies of the anisotropies. Anisotropies that were measured for the first time 25 years later by the Kobe mission. And then we had WMAP and Planck that improved the angular resolution and measured polarization. So since I am a theorist, I like this time scale of 25 years because it's somehow encouraging. It gives an indication of how sometimes predictions anticipate observations and maybe provide a guideline for them. So what we have here on the right is for the moment not too much. What we have are, so we expect to detect a monopole in the next few years, maybe with LIGO Virgo for sure, and pulsar timing array. for sure with Einstein telescope. For the first map of the anisotropy, we need to wait for the next generation or to try to use alternative detection methods like cross correlation or something else like astrometry or atomic interferometry. What we have for the moment are works on the theory side. So we have theoretical predictions. So we are somehow ready once the first data will arrive to perform a first comparison. We're on the way to first comparison with observations and hopefully extract from this observable some astrophysical information on galactic and subgalactic physics. And with this, I conclude, and I thank you for your attention.
Thank you, Giulia. So, do we have questions? Gary.
That was a wonderful talk, Giulia. It really opened my eyes. So I have a technical question about the next generation, Einstein telescope and Cosmic Explorer. So if I understood correctly, so to get the to get rid of the fluctuations, you need two set of antennas, so it's very unlikely that you'll have noise coming from both sets at the same time, unless, I was wondering, could the sun make an influence? Could the sun be a source of noise?
You mean?
Yes, of common noise.
Of the sun.
I don't know, some fluctuations that could the sun in one way or another be a source of noise in this combined effect? I think François wants to answer.
I know that they have a way experimentally to get rid of an effect due to a fluctuation of our local gravitational potential. So I assume that this is affected by all the other celestial bodies around us. So I don't think that this is a problem, but I can't tell you now what they do in order to get rid of this. But this is taken into account.
I wanted to have some comment on one of the assumptions you made when you were looking at the cross correlation of the signal with spatial angular distribution of galaxies. Just did say it explicitly because this is uncorrelated with the cosmology, but cosmology has to propagate through large scale structures, so it's actually non-correlated. I mean, we have well-known cases like integrated sex wolf, all of this. So I'm just puzzled by the assumption that seems to be wrong.
No, so we didn't assume that. So, but it's true that I was saying that the cosmological background is not correlated. I should have said is less strongly correlated.
Okay. Well, that makes more sense to me. Thank you. I was very puzzled by this because
it was an abuse of language. Okay.
Irina, now. Merci.
Thanks, Giulia. So my question was about what redshifts are important for omega GF. So you say it's an integral over redshift. So what redshift does the contribution peak? And I guess similarly, what kind of galaxy catalog would you want in terms of redshift properties in order to make such detection?
Okay, so we are collecting contributions from all redshifts, but then you can, in our prediction, you can decide to plot contributions from different beings, and it turns out that you are dominated by a contribution. So the monopole is dominated by a contribution around the redshift 1 and 2. So you follow the star formation rates, and you get the maximum amount of signal from the peak of the star formation rates. While if you look at the anisotropy, then depending on the astrophysical model you have, you get that different angular scales are dominated by different redshift beings. This is why the study of anisotropy in principle could also help to have some type of redshift information.
We have one more question here.
Thank you for the very nice talk. Concerning the technique in which you use pulsar timing, can the same technique, or has the same technique been applied to other entities with the same property of periodic characteristics?
Other entities, you mean instead of pulsars,
something else like Cepheids or something else with a repetitive characteristic?
Question. Not that I know, but I'm not an expert, so I'm not sure. It's not really the periodicity in time, but something that has been proposed is to use astrometry, so to monitor the position of, like with the instrument like Gaia, the position of stars in the Milky Way for a long time. And if you see that this position gets perturbed, this could be the signal of the fact that a wave has passed by. But for the time periodicity, I can't tell you.
Ah, derrière toi, Irina.
Yes, thank you for the talk. I was just curious about the theoretical modeling of the power spectrum. So you assume the cosmological part is fixed because preceded in cosmology, but some would argue it's not so clear. Do you have an idea, a rough idea of how much it changes when you change cosmological parameters in the modelization of this power spectrum, or?
But I would expect variation to be totally subdominant and negligible with respect to what you get from the
Okay. Also regarding this variation of astrophysics, so there was this plot where you showed individual parameters, how it affected, and it seems like everything is so degenerate. It's so yeah, it looks like all the parameters have similar effects on this power spectrum. So do you have other probes that could help break these degeneracies, not even considering the?
I think that you mean that everything gives just an offset.
Yeah, exactly.
Yes. If you change the redshift distribution of sources, like with this model here, where we change the initial separation of binaries, then you change the redshift distribution, and then you get features in the angular power spectrum besides a global shift. To answer your question, I think that if you go on and you consider all possible cross correlation between this observable and galaxy count, lensing, and so on, then you could try to break these degeneracies.
Okay, thank you.
Alors, je ne sais pas comment tu fais, mais il semble y avoir dans la discussion le commentaire de Benjamin. Moi, je le.
Yes, there is a bunch of comments that Ben posted as a response to the previous question. Ben, do you want to say something, or should I read the comments?
Sure. No, it's just it's an interesting comment and question. But so I looked at this briefly and actually asked some people that are interested in in stellar pulsations or other kind of repetitive phenomena on small scales, and it just seems that, so I was interested because pulsars, millisecond pulsars, are far and few between. But they're extremely accurate. And I thought maybe one could find other kinds of clocks that, even though less accurate, would win just because you have many, many of them, thousands, maybe, many orders of magnitude more. But it turns out just millisecond pulses are so much more accurate than any of these others, other clocks, that, as far as I know, there's no alternative that's competitive.
Attends, on a d'abord une question là-haut.
Yes, so you described well the sensitivity which is required to detect the monopole, but there is also the question of the amounts of data, I guess, that you need to detect it. The amounts of data that you have in LIGO Virgo. So my question is in the design sensitivity of LIGO Virgo, how many months or years of data do you need to detect the monopole?
So when you plot the sensitivity curves that go better and better, you take into account the fact that which is the integration time, the observation time you are considering. So this curve will go down if you of a factor 10 if you increase square root of 10 if you increase so you go from 1 to 10 years. So they scale with the observation.
Yes. So your guess is how many months or year do you need to detect the?
That, so now I will embarrass myself because
I don't
remember when it's the final sensitivity. Maybe somebody in the audience knows. This plot. here. So the design sensitivity will be reached in a few years. I can't remember if it is 5 or even I don't remember that. Well, I don't know, but it's kind of moves anyway all the time. But so the curves there are for 1 year from the date.
Mm-hmm. So one more question by François.
Concerning the integral constraints on the integrated effect, as you pointed out, this is the same effect that we have for the infrared background. And the curse there, as we all know, is that we have one integral constraint for many very large parameter space of the redshift distribution, whatever. So if you make the most simplistic assumptions of power laws, that is any of these integrating function is just parameterized by 1 or 2 parameters. What is the total sum of parameters or the dimensionality of the space that you are trying to constrain with one number?
What number you mean, one monopole?
Yes, the one that you are expected to constrain within my lifetime. So is this like a 5-dimensional space, 6-dimensional with one integral constraint, or just for me to? Because the CIB was a curse for the CMB. Sorry.
Let's see.
And as always, a curse can also be a good thing.
So this is the function that you would like to constrain, because this is an astrophysical kernel that is already, it contains everything hidden inside. It's a function of frequency and redshift. So if you assume that the frequency is power law, like it is the case in the Hertz band, then you can get rid of it and just focus on the redshift dependence. Okay. And then you could try to find a parameterization like a Gaussian kernel for this guy. And so in that case, you would have 3 parameters. The global amplitude, the mean, and the then, of course, these are effective parameters that you need to relate.
And then you still have to add the next layer of parameters to relate this to the underlying population of sources. These pesky astrophysics.
Do we have more questions? No. So if no, then let's thank Giulia again and welcome here. And she's in office 133B for a long time, so don't hesitate to discuss with her.
Non, c'était très bien. Il y a un moment, j'ai pensé un peu, j'ai oublié. Very, very nice. Really.